All right, for the BC students, picking up where we left off, where I was so rudely interrupted by the bell, I think I left you guys kind of at this point, so I'm going to go ahead and join you. Our objective at this point is to find an expression that represents the area in one of our rectangles. So I'm just going to pick on the kth rectangle. So to find the area, I want to know what's the width. Well, that's a change in x. So I'm going to put delta x, and I'm just going to put a subscript of k just to represent that I'm in the kth rectangle. And the height of the kth rectangle is determined by the functional value f evaluated at c sub k. So if we want an area expression for the kth rectangle, it's going to be your base times your height. It's going to look something like this. So that's the area for the kth rectangle. So let's look down here at this expression that we next want to kind of observe what's going on. Okay, this is the area in just the kth rectangle. This right here sums all the triangle or all the rectangles areas from k equals 1 to n. So if I had 50 rectangles, that sigma notation is going to sum all the 50 areas. And that's what that says right here. All right, so moving on next. All right, so let's look at the definite integral. I've kind of alluded to that before. The definite integral is the integral that has limits, upper and lower limits, and represents area from a curve to the x-axis, from a beginning x to an ending x. So I just kind of informally told you guys that before, but here's actually a description of what's happening. The method of summing rectangular areas allows us to approximate the area under a curve. To calculate this area exactly, we would need an infinite number of infinitely thin rectangles. The limiting process of the Riemann sum, and remember, Riemann sum is just an addition of areas in rectangles. Okay, to find a limit of the sum of those areas allows us to express the exact area under the curve. And it's given by, okay, what I want you to do is about halfway here on the line right here. What I want you to do is I want you to recopy this, this notation right here. Let's put it about right here. All right, so we have the area sum from 1 to n rectangles, so that's a bunch of rectangles. Okay, I'm going to find the limit of this Riemann sum. This is called a Riemann sum right here because you're adding the areas in a finite number of rectangles. But what I'm going to do is I'm going to find the limit. So in front of this sigma notation, I want you to come over here and I want you to put limit as n approaches infinity. N represents the number of rectangles that we're going to inscribe from our beginning x to our ending x, the number of rectangles we're going to inscribe. So we want that value to go to infinity, have an infinite number of rectangles. And then we want to say that the delta x right here approaches, and think about it, the width of every rectangle, well, if there's an infinite number, it has to go to 0. They have to get infinitely thin, if you will. So this is kind of an interesting limit because we have two situations occurring here. So let me go backwards here and say, okay, you know what that's equal to? That's equal to the area in each and every one of the rectangles that you could possibly fit from A to B. That's an expression that represents the area in all the triangles. So a limit of a Riemann sum, it actually over the years has kind of evolved into some other kinds of notation, but that's represented by the definite integral. So this whole expression right here kind of evolved into, all right, let's integrate the function from A to B, and that's going to actually give us our area. Okay, this is an expression that represents the area under the curve to the x-axis. That's a definite integral because it has limits. Okay. Now, in the future, we're going to be figuring out how do I find the exact area without having to approximate using rectangles or triangles. And that'll come in a later day. Okay, so but for right now, as we build to that point, okay, I just wanted you to see that the integral evolved from the limit of a Riemann sum, areas in rectangles. All right, one of the homework questions is just for you to kind of pay attention to notation and see how we can rewrite it as a definite integral. So a kind of question that you're going to see is express the limit of the Riemann sum, this, as an integral. So I want an integral if P, down here, P denotes a partition of the interval from -1 to 3, A to B. So P is just being replaced P is replacing the delta x that we had up here. Okay, so our limits go from -1 to 3. We're going to have to be told what that interval is. Okay, and then we notice that rectangles are going to get infinitely thin. The width of each rectangle approaches 0. Okay, and if you look at this right here, this is the function. That's the functional value, and this is the width of the kth rectangle. So in a definite integral, what I'm going to do is I'm going to replace the c's with x's. So c sub k is going to get replaced with x. So I have 3x squared minus 2x plus 5. The delta x sub k is the differential in x. And that's kind of how it's evolved over the years. So remember, this is height, and this is width. All right, so just some notation, some things that I think, we should look at. All right, at this point, I'm going to say, you know what, let's switch gears. I'm going to come back to this later. We'll fill in this bottom part of the worksheet at a later time. But right now, the next thing I want to do is I want to visit some properties of integrals. Some of the things that you can do or are allowed to do, properties of integrals. So if you want to turn this worksheet over or get your own notes out on a clean sheet of paper, we'll go from there. We're going to look at 5 properties. Consider the integral from lower limit a to upper limit a from f of x to the x-axis, wherever f of x is. It might be above the x-axis, it might be below, I don't know. Okay. If you have a beginning a and an ending a, if you're guessing what's the value of this integral, it has some value tied to it. Okay, if you guessed 0, you're absolutely right. When the limits are the same, the value of the integral is 0. So whenever you're studying an integral, a definite integral, it's probably pretty important to pay attention to the limits because the answer might be as easy as 0. Okay, I just want you to notice the limits here. We usually start with a at the bottom and b at the top. A usually represents the smaller x value, and b is the larger x value. All right, so what effect on the answer would I have if I put the bigger x first and the smaller x last? Well, instead of working from left to right and accumulating the area, if you will, we're working from right to left. So if you had to guess what effect that has, well, it's actually going to be the opposite of what you would have got had you integrated or collected or accumulated the area from left to right. So it may become necessary for us to switch limits, and if we do switch limits, it's important to note that we're going to find the opposite of the answer, and that will come up. All right, I'm going to go ahead and just give you this next property right here. If you are asked to consider an integral from a to b of f of x, let me get a visual over here. Let's just say we have this function. Here's a, and here's B. Maybe. Okay, so we're interested in this region right here. Okay, well, what I could do, it might become necessary, is I could determine any C value between A and B. I could maybe say, well, here's C. Consider the line x equals C. Okay, I can break this apart, if you will. I can say, you know what? Let's just integrate from A to C, collect that area of the function, f of x, and then I can collect this area by itself right here. So this integral would start with a lower limit of C and end at an upper limit of B. Same function. I could divide this up into many sections, but go back and add them together, and it'd still give me the same value as that integral. And we'll work with that property too. Let's look at number 4. Consider the integral from A to B. Consider K to be a constant multiplier times some function. All right. If we wanted to make this work easier, simpler, make the numbers smaller or better. Okay, if K is a constant multiplier, there is a property that allows us to factor out, if you will, pull out, divide out, bring out of the integrand the K, if it's a constant multiplier. I can never bring out a variable because there's some calculations that I have to do with that variable. I can't ever bring out a variable from an integrand, but I can bring out a constant multiplier. But don't confuse that with if I were adding a constant, okay? I wouldn't bring out the constant if I'm adding or subtracting, only when it's a multiplier on the integrand. So that's our 4th property. Our 5th property, okay, I'm going to give you our 5th property, even though we've already actually been using it. It'll make sense to you. Consider the integrand that is a sum or a difference of 2 expressions. Sometimes it's going to be helpful to break apart. If I'm adding or subtracting, it might be easier to work individually with each of the functions. So the integral of a sum is actually the sum of an integral. So both f and g would get the same limits here. So sometimes it's helpful to break it apart in our work with integrals. Okay, so next time we meet, we'll get to practice these properties and get to practice what we did on the worksheet as well, looking at a limit of a Riemann sum.